C, what's the C for?
Christopher.
Oh, Matthew Christopher Russell, who speaks about the very long title, Using Mathematics to Conjecture and Prove Theorems in the Theory of Partitions and Commutative and non-commutative recurrences. And because the title is so long, we have an extra minute.
Okay, thank you all for coming. I appreciate everybody here. Let me just say, this is a slides talk, not a chalkboard talk. Sorry, Dr. Z. And so there's always the temptation with slide talks to go faster than I should. So if I say something that isn't making sense, please interrupt or whatever. Drew, please feel free to speak up as well. Of course, you have the time afterwards to ask questions. Okay, so let's see. I guess that, so this is outline for the talk. I guess instead of just looking at just simply stating my results, I'm going to try to group it because my results are in a bunch of different fields. I'm going to try to group it kind of by the type of experimental mathematics I did in each chunk. So one part would be about experimentation, one part would be using experimental mathematics, using computers to guide my proof when I do things. And then finally, we will see some cases where I can even use the computer to automatically prove theorems, but without any real human input. And then the areas of mathematics involved will include partition identities, and also recursions and Laurent phenomenon, and we'll see those in both the commutative and non-commutative cases. Okay, so first off, experimentation. And then, so this was most common in my partition identities part. So here's a definition of a partition of n. It's a finite non-increasing sequence of positive integers that add up to n. So for example, there's 7 partitions of 5. You can verify for yourself. Note that we do not, so we assume that we go from biggest to smallest. So you can't say, 1, 3, 1, that's already covered by 3, 1, 1. And then, so one question is that you can ask is, how many can you quickly tell me, how many partitions of 1,000 are there? That is one sort of question you could ask. You can also ask about restricted partitions. So suppose that I put, I say, you can use any partition you want, but there's also going to be some restrictions. For example, you might only allow certain parts. You might only allow only odd parts to be used. Another sort of restriction you can have is how do the parts interact with each other. So for example, you can have only distinct parts, you could say. So distinct parts means you can't repeat any parts, so the parts are interacting with each other. You have a 5, you can't have any more 5s. So let's take a look at how many partitions of 5 there are under both of these restrictions. So there are 3 partitions of 5 that are odd, so only use odd parts, 5, 3, 1, 1, and 5 ones. And there are 5 distinct partitions, or sorry, there are 3 distinct partitions of 5. 5, 4 plus 1, 3 plus 2. All of these 4 partitions repeat some part at least twice. And you'll see there's 3 on the left and 3 on the right, and that's not a coincidence. That's a theorem that goes back to Euler that says for all positive integers n, the number of partitions of n into odd parts is the same as the number of partitions of n into distinct parts. So how many partitions of 1,000 are there into odd parts? I don't know off the top of my head, but it's the same as the number of partitions of n into distinct parts. So this sort of statement is kind of like our most prototypical example of a partition identity. The number of partitions of n into one restricted type exactly equals the number of partitions n into some other restricted type. And so we will call these product sides and sum sides. Product sides are going to be partition and a part that satisfies the congruence condition. So odd parts are parts that are congruent to 1 mod 2. But we can have that more generally. We call this the product side because we can write in its most usual form. We write their generating function as a product of 1 over 1 minus q to the m over some set of m. And I just wrote it very generically as m is at least 1 and m satisfies congruences. So here is one example where we have m is at least 1 and m is congruent to plus or minus 1 mod 5, 1 and 4 mod 5. Some sides, this is going to be kind of how do the parts interact with each other. And so the most simple, or kind of the generic way for doing this, the first condition that we want, is difference d at distance k. And so what I mean by that is for all j, so here these are lambda sub j and lambda sub j plus k. This is the jth part in our partition. This is the j plus kth part in our partition. We want this difference to be at least d. So before, when we had so we saw the distinct parts, that's our one example so far. This just works by setting k equals to 1 and d equals to 1. So that will make sure that all your parts are distinct. And then so that's exactly what I just said there. Euler's theorem has difference 1 and distance 1. We'll also want to have some sort of initial conditions. We don't see that in Euler's theorem, but we will quite often say that certain subpartitions are forbidden. So I won't give a technical definition of subpartition. It's just if you have, take a partition and take some subset of the parts, that's a subpartition. So you could just say 1 is not allowed. You can use so you can use any parts you want, but you can't except for 1. Okay, so we can kind of, using all of this language, we can restate Euler's identity. The product side is 1 mod 2. The sum side is just difference 1 at distance 1. The next most complicated after, so Euler's identity is mid-1700s or thereabouts. Rogers-Ramanujan. Rogers first discovered it in the 1890s. Ramanujan rediscovered it in the 1910s. Here, the first one, the product side is plus or minus 1 mod 5. Hence why I use...
want to discover a Q identities.
Right.
Data amount, not this.
Right. Yes. Exactly.
It's introduced to McMahon.
Yes. So Rogers-Ramanujan, and I guess on this note, Rogers and Ramanujan both discovered this as a Q-series identity that was only later shown to have a partition theoretic interpretation. So here the product side plus or minus 1 mod 5, and the sum side is a difference 2 at distance 1. So the interpretation here is you have a part, if 5 is in your partition, not only can you not have any more 5s, but you can also not have any 4s or 6s as well. The second identity has, on the product side, plus or minus 2 mod 5, and the sum side has the same difference to a distance 1 condition, but now we forbid 1, so all parts must be at least 2. And so I said that one, 1890s for the first discovery, 1910s for the rediscovery and when people really got interested in it. And so now we want to fast forward to 1990, give or take a handful of years, when Stefano Capparelli, one of Lepowski and Wilson's students, in his PhD thesis, he was doing some study of affine Lie algebras and managed to conjecture a new partition identity. And so the product side you're allowed to use plus or minus 2s, plus or minus 3s mod 12. That's all nice. The sum side is a difference 2 at distance 1. And 1 is forbidden as a subpartition. But now we have a third sort of condition here. We have an added congruence condition here. If consecutive parts are within 3 of each other, then their sum must be a multiple of 3. So for example, so we have this difference to a distance 1. So that says, so if we have 5 and 2 in our partition, that certainly is okay with the difference to a distance 1, but 5 and 2 are within 3 of each other, and 5 plus 2 is not a multiple of 3, and so 5 plus 2 wouldn't be allowed. So we have this extra congruence condition. This is another way that we see the parts interacting with each other. And so this kind of suggests that we need to rethink what our sum sides look like. So we can still keep this difference d at distance k component for all j. Lambda j minus lambda j plus k is at least d. Our initial conditions are still going to be for bit sums, small set of subpartitions. And we're going to have these congruence conditions. And so this is the way that I'm going to look at this. So for all j, lambda j minus lambda j plus a is at most b, only if the sum of lambda j up to lambda j plus a, all of these parts in between, is congruent to something mod something. So for Capparelli, we would say that we have lambda j minus lambda j plus 1 is at most 3, only if lambda j plus 1 is congruent to 0 mod 3. So that is the sort of framework.
So A, B, C, and D are enough to specify Capparelli?
Right, yeah. So, yeah, and you even get the special case, the kind of special case here, where A is 1 and C is 0. Those are kind of the simplest cases that you can consider here. Because obviously A has to be at least 1, just look at the adjacent parts, and then 0 mod whatever, that seems to be the simplest that you could come up with. So I've been talking a lot. Let me just pause, see if there's any questions. Okay, so this is all, everything I've gone through so far is basically background information. And now this is kind of where, so I probably should have said this earlier, this part of the talk is joint with Shashank Kanade. So this is where we thought about how can we experiment with this. So if you take a look here, there's a lot of parameters that we can play around with. There are 1, 2, 3, 4 parameters down here. There's a couple up here, and then we can think about come up with some set of some set of sets of subpartitions to iterate over. And so the point is that we're just going to we're just going to sit down at a computer and have the computer calculate out sum sides for all of these different combinations. I guess there are a couple more little preliminary stuff. Euler's algorithm is a very useful tool here. I'll give you some power series. So here, this is just a generic power series with coefficient constant term 1. So it gives you, if you feed in the sequence of bn's, it factors it for you in this sort of form, and that will be very useful for us. So yes, this is the slide I started to talk about 30 seconds ago. So we brute force calculate initial terms of very many sum sides, and so this is exactly as advertised. We, at times we were doing this probably for a million different possible sum sides. We were just, very simply, without too much thought, come up with all of these different combinations, iterate over some range of values for our 6 or 8 parameters, and then calculate out, in different versions of our program, sometimes 12, 15, 30, 40, whatever different, the initial terms of our sum sides. And we get, so we get something that looks like this. And from a previous slide, we factor this out. And And the question is does this give a periodic sequence of A sub n? And hopefully, so for any sequence that you make up any B sub n sequence that you want, you can come up with the corresponding A sub n sequence. But if you give it, most of the time you just start feeding in numbers, you'll get gobbledygook. This will, the A sub n terms will get quite large. They'll flip back in between, positive, negative, and stuff like that. We want periodic sequences of A sub n, and ideally they would all be zeros or ones, because that would correspond to either this appears or this doesn't appear. That's our nice partition generating function into certain congruence classes. In other cases, we may allow other small, maybe some small positive terms or -2 and stuff like that. But in general, 0 or -1 or 0 or 1 is what we're aiming for. And so after doing this a million times, or however many times it was, we managed to find some mod 9 identities that are new. And so here the product sides 1, 3, 6, or 8, mod 9. The sum sides difference 3 at distance 2. We also have a consecutive parts are within one of each other. Their sum must be a multiple of 3. And then there are 2 more that are like this mod 9 identity. The product side, so before this was plus or minus 1, plus or minus 3 mod 9. This is plus or minus 2, plus or minus 3 mod 9. And the product side, the sum side is also very similar. Difference 3 at distance 2. The same congruence at a distance condition. But then we also don't allow you to use any ones. The third one, plus or minus 3, plus or minus 4. And you can kind of guess what's coming here. Same, and now we are forbidding both 1 and 2 as subpartitions. All 3 of these, so we simply conjectured them with very good numerical evidence. This is experimental mathematics. I may say as heart. We are literally doing computer experiments in mathematics and just seeing if we can make any discoveries. And here are.
And you also prove them. We prove them. We didn't mathematically prove them.
Right, but yes. We are very certain that these and the following ones are all true.
You check it. There's 1,000 times.
These are up to 2,000. Wow. Yeah. So.
But there's no proof.
There's no proof.
Yes, there is. There's no mathematical proof.
And it's not just Shashank and I that have tried to prove it. I know other people have certainly looked at it as well and have not been able to produce a proof. Okay, so we also have some asymmetric mod 9 identities. So now you will see that the product sides here are not just plus or minus 1, plus or minus 3, or something like that. 2, 3, 5, 8 mod 9. Sum side, same difference at a distance. If consecutive parts are within one of each other, their sum must be congruent to 2 mod 3. So this might be, I don't know if I should say this because I didn't rigorously check this, but I don't know off the top of my head of any partition, other identities that have something that looks like that, where it's not a 0 in there. And then 1 is forbidden as a subpartition. This one comes with a friend, I4A. So you'll see this is, the product side here is exactly the ones that aren't included up here, other than 0 is, we don't allow anywhere. The sum side, that looks familiar. This 2 becomes a 1. Again, that no surprise, so that kind of changed. But then we have this kind of unusual initial condition. So you can have 1s in it, you can have a 2, but you can't have 2 2s. That's the only initial condition. We also found 4 mod 12 identities. 1, 3, 4, 6, 7, or 10 mod 12 is the product side. The sum side here, we go up to difference 3 at distance difference theory distance 3. And then here is the congruence at a distance. So now instead of having different distance 1, we have distance 2 here, lambda j minus lambda j plus 2. And then we want all 3 of these, so we're including the sum of the middle part here. This has to be 1 mod 3. 1 plus 1 is forbidden as a subpartition. The product side here is exactly, so this one is a friend of the previous one. The products here are exactly opposites. 11, so minus 11 is 1, minus 10 is 2, and so on and so forth. Mod 12, difference theory at distance 3. That 1 mod 3 becomes a 2 mod 3, and then we have some forbidden subpartition. So here's 2 more that I won't talk about because we already done examples. Yeah, Brock.
When you derive the second set of product side and sum sides, do you actually when you said that you have 11 there, you have 1 there, 8, 4, and so on?
Yeah.
Are you deriving the second set from the first set, or you're?
Yeah, there's actually an interesting sort of thing here. So you know, everybody knows that our numbering went I1, I2, I3, I4, I4A, I5, I5A, and so on and so forth. That's because I1 through I6 we found first, and then we later went back in and found I4A, I5A, and I6A. And so we so this is based off a conversation I had with George Andrews at Penn State. He kind of suspected that it's based off of this sort of thing, there probably should be another one that looks like it. And so he kind of suspected that if we have these sum side conditions, it's just, that if this is an identity, then this should be an identity, and we're not really, but you have to find the initial conditions yourself.
It's not known how to get one identity from the other, manipulated.
I don't think so. I would suspect if you actually prove this, you would prove the 2 simultaneously, but or prove all 4 of the mod 12 identities simultaneously.
Well, if you multiply the 2 product sides together, then you've got all the.
Yeah. I've
thought
that
idea too, but
yes.
Nobody seems to like it.
Yeah, yeah, I remember that conversation. It is an intriguing thought, but I'm not sure where it goes.
I agree with you.
Yes. Okay, so this is so that kind of wrapped up the first part. Going to switch over to now not just conjecturing new things, but now a little bit of guiding proofs. And so here I'm going to talk a little bit about motivated proofs of partition identities. So we have the 2 Ramanujan generating functions here. And so one thing that you can do is that if you realize that term by term the coefficient of up here is bigger than the coefficient up here. So 3q to the 7th, 2q to the 7th, 3 is bigger than 2. And if you look at the sum side words, that's easy to see. Difference 2 at distance 1, difference 2 at distance 1, and you're not allowed to use any ones. So any partition down here is also counted up here. And so back in the 80s, Leon Ehrenpreis had a question can you come up with this inequality just from looking at the product sides? So I don't tell you what the words are. In some natural and some motivated way, can you come up with that? And again, in the late 80s, Andrews and Baxter managed to come up with a what they call motivated proof based off of this concept. So we call G1 and G2 to be the 2 Ramanujan generating functions. Well, we subtract G2 from G1, as stated before. We're going to get all non-negative terms. And it's going to start with a Q. So we can pull out the factor with Q here. And then we can define G3, was their idea, to be G1 minus G2 divided out by the factor of Q. And now we have 1 plus Q cubed plus more stuff. And it doesn't take too much imagination, I won't go through the argument, that this is just generating function partitions with difference to a distance 1, and all parts at least 3. And you can continue down that trail by defining a sequence of these generating functions. G sub I is G sub I minus 1 minus G sub I minus 2, divided out by the appropriate factor of Q. And it's always going to be the corresponding words, and it's always going to start off 1 plus Q to the I plus other stuff.
But the coefficients of G3 are not all 1.
Right, yeah. This was as far as I wanted to go to squeeze to fit on the slide, but yes. It should not be, I guess that is a little bit misleading to make it look like it is all 1, but that's not the case.
Well, there's no
Right.
cube squared, so.
Right. So another project I worked on was different people have produced, been busy producing motivated proofs of other partition identities. So I participated in a project where we provide motivated proof of Andrews pursue identities. So here the product side is everything that is not congruent to 0, or plus or minus k minus I plus 1 mod 2k. So this is pick any k you want, at least 2. And there's going to be k different identities here. The sum side difference, at least 2 at distance k minus 1. And then this is if you kind of max out the numbers of let's say 9s and 10s, so you can have most k minus 2 9s and 10s combined, then the sum of all your 9s and 10s has to be something mod 2, and this tells you what that has to be. And most k minus I parts are 1. There's our initial condition. And so we wanted to try to provide a motivated proof of this. And so it took a while, but computer experimentation was kind of key to getting this going. We ended up looking at, so if we could let b sub I be a generating function for the sum sides, and bi tilde was going to be a generating function for sum sides with the wrong parity condition. So just copy paste all of these lines here and add in a plus 1 right there. And so using this, I think these are the calculations that we came up with for k equals 5. So here are all of the generated functions. I only show up to q to the 8th. I think in practice we did this out to like q to the 40th power or something like that. And so using this data, the goal was just to try to find what linear combinations of all of these series works to let you have the empirical hypothesis that stuff cancels out and you get all positive, all non-negative coefficients, and stuff like that. And so after some experimentation, we figured out that this was the proper setup. That b tilde sub 5 was also equal to b4 minus b tilde sub 5 divided by q. We call that b6. B tilde sub 4 minus b sub 5 divided by q was also equal to b sub 3 minus b tilde sub 4 divided by q squared. We call that b the 7th, and we verified all of this stuff here. And I should say, not only that, but for all of these that we came up with, these new definitions, the appropriate empirical hypotheses, 1 plus q, 1 plus q squared, 1 plus q cubed, and so on and so forth, those always held. Also, I don't have time to thoroughly go into this, but we also, all of these b's and b tildes correspond to the higher shelves. And so there are, the sum side words are still what they are supposed to be. And much like in Andrews and Baxter's original proof, and much as in the Pasky and Jou's motivated proof of the Gordon idea. So that kind of, let me just pause here to see if there's questions. So far, we've,
So
yeah,
this
please,
is related to so many